Okay, so I think Rong is in the call. Okay, so could you prepare your slides? So while I'm introducing. All right, so it's my pleasure and honor to introduce Dr. Rong Jin. Uh, Dr. Jin is currently an associate director of Daimo Academy at Alibaba. So Daimo stands for Academy for Discovery, Adventure, Momentum, and Outlook. And he's leading the research and development of state-of-art AI technologies. So before joining Alibaba, Dr. Jin was a faculty member of the Computer Science Engineering Department at Michigan State University from 2003 to 2015. And his research is focused on statistical machine learning and its application to large-scale data analysis. He published over 300 technical papers, and mostly on top conferences and journals. So among his broad research topics, I think the one of his expert is in deep metric learning, which is highlighted by just a few recent publications like soft triple loss or deep metric learning under uncertainty, and also the application or dataset which he owns, like 100 million Alibaba classification dataset. Dr. Jen is an currently associate editor of TPAMI, IEEE TPAMI, and also ACM transaction at KDD, knowledge discovery from data. Dr. Jen obtained his PhD in computer science from CMU, and he received NSF Career Awards in 2006. And he also received Best Paper Award from Colt Conference on Learning Theory in 2012. Okay, with that, let me hand it over to Dr. Jin for his keynote presentation.
All right, thank you everyone for attending this talk. So today I'm going to talk about the improving the instance classification by representation learning. So outline my talk. First of all, I'm going to discuss representation learning in the case of image search. So this includes the large scale image search and instance search. Then I'm going to focus on the representation learning by itself using the example of ReID. And I'm also going to discuss how to effectively leverage the class information in the training data for the better representation learning. All right, so in Alibaba, we have this product called the PyLitao. Basically, this is an image search product for e-commerce, and so you can basically take the image, and the system will be able to map the image to the product, and then identify the appropriate shop websites for the product, and you can just go directly to that website for shopping. And here's the small demos just to show how the PyLitao can be used for your daily life. So one of the challenges that we're facing here is large scales. As you can see, we have 400 million products. We also have over 3 billion of images and 20 millions of daily active users. So this is a gigantic system you have to deal with. So as I said just a moment ago, the challenge we face in building up the PyLitao system coming from two perspectives. One is the scale, right? The number of the images you deal with, the number of ID, the product ID you have to deal with. Also, we have to build a system that can scale to 20 million users on daily basis use. On the other hand, as a consequence of this large data set, is a subtle difference because many of the products actually bear a large similarity, particularly for the products that been created by the same brain or by the same manufacturer. They have a very similar visual appearance, even though they belong to different product ID. So all this actually cause difficulty in the image matching and such. Now, at the very beginning, when we're developing the system, we do not have enough training data to build a very comprehensive representation for images. But at the same time, we do actually have a large amount of user feedback data, which is the user click data, that we can leverage. Now, at the very first time, we thought that the click data would be a good indication about visual appearance in the query image versus the visual appearance in the clicked image. But turns out the assumption seems to be wrong. In many cases, the image clicked by the user tends to have very different visual appearance compared to the query images. And then we realized that based on our observation, the co-click data seems to be a much reliable signal in terms of identify the similar products. And so what I mean co-click information is that when you issue the queries, the user clicked multiple image in the return results. It turns out those clicked image tends to have large visual similarity and sometimes even belong to the same product ID. So we utilize the co-click information as a basis to construct supervised information for the representation learning. The idea is very straightforward. So we can build a graph or eye-to-eye, item-to-item matrix based on co-click information come out of users' behavior. And then you can run the graph-based clustering algorithm to partition this huge database into large number of clusters, and those clusters will form the pseudo labels, allow us to train a better representations. Now on the right side of the screen, as you can see, there was a table showing the results here. So if we simply just using the attributes, the results is really poor for top one. But if using the training data with the deep ranking algorithm, you can beef up the performance to 45% accuracy for top one results. But if you add in this additional co-click information, then you can further move the results to 48%. So that really indicates that the usefulness of co-click information in terms of supervising the representation learning for images. Then second information we try to leverage is those site information, because for many of the products, not only they provide images, but also they provide the titles and descriptions. So it would be nature to utilize those site information as the guidance to learn properly the representation for images. But quickly we realized that for one reason versus the other, those title and description generated by the manufacturer does not necessarily provide accurate description of those images. Directly using them without any discrimination seems to harm the performance rather than improve the performance. So we then devise an algorithm try to identify those images tends to have inappropriate annotation from the text. So the idea is very straightforward. So basically we have two types of representation. One is based on the visual content, the other one is based on the text description. By looking at the discrepancy between these two representations, we may be able to figure out which image tends to be noise, which image tends to be more accurate annotated. So more specifically, we're using the KNES label as the basis. So for each image, we can using the visual content as the way to rank these labels. We also can use the textual content as basis to rank these labels. Now, if you see a large difference in the ranking results, then we believe this image is likely to be noise annotated. Therefore, its importance to be lower. On the other hand, if the consistency between these two ranking lists is high, then the likely this image is accurately annotated, then we would like to give even higher weights for those images. And that simple algorithm of distilling the noise tends to give us good performance boost in the results. So here are the evaluation on some benchmark data set. One is the closing 1 million data set. The other one is the data set Ali products, which are generated by our team. So as you can see, by distilling the noise from the data, we are able to improve the performance by more than 1%. In fact, this is the key algorithm that we utilize in the Web Vision Challenge 2019, and this is the algorithm allowed us to win the first place. And then another challenge when we deal with the large image data set is the heavy tail distribution. As you can see from the right up corner of the plots, you tend to have a very large number of images associated with the product that are very popular. But when you come to the heavy tail product, you will see a small number of the images associated with those products. And that actually will make us make it difficult to train a representation that can work well for both the popular categories of products as well as the less popular category of products. Now, in order to address this problem, we again leverage the site information. So we sort of come up with a two representation for each of the images. One is the visual content, and the other one is the representation coming from the text description. Turns out by nicely combine these two representations together, it actually gives us a significant boost for those the images on the tails. So as you can see from the table, that for three different data sets, if we look at the head class, adding the texture information, you will observe relative small margin improvement in the performance. But when we examine the performance over the tail class, we actually see a substantial performance gain due to the introduction of this additional texture information. So this very simple approach allowed us to beef up the performance, particularly for the tail class. Now, for our group, we actually made this image search product not only just available for the internal use, but also it is now available over the Ali Cloud. So people can download for free trial use. Also, you can purchase that. It's going to charge you by monthly fee based on the size of your repository. And the other very interesting application that we use for this image search is on the Xianyu. So in the Xianyu, people often sell the second-hand product. So it's going to be very time consuming and the challenge to fill out all the product related information like attributes. Now, this is the moment the image search can play a very important role. The system will be automatically identify related product and fill out all the associated attributes. Now, it's very worthwhile to mention that our method is not only just provide the way to fill out the attributes and information related to product automatically, but also it actually can actually to estimate the selling price that seems to be more reasonable on the market based on the previous the transaction informations. And then finally, we utilize this image search technology on the shelf product, the shelf product recognition for the retail business. And so this is a function that you can take the picture of the shelf. The system will automatically recognize all the different products being laid out on the shelf, and it's also be able to come up with the statistics tells you which products are being laid out on which layers, and so on and so forth. Okay, so this is roughly the part relates to the image search. Now, I also like to come with the second part, which is the instance search. So the idea of the instance search is that you probably have a query of arbitrary object, like what we see from this example that the interest object is the bag with this young man. And then you have been given a gallery of images, the video sequence captured from multiple cameras. And the goal of the system is to output the image video frames containing the query objects, also with the bounding box that accurately indicates the location of the object, as you can see from the return results. Now, the standard way to do this instance search would be comprised of two components. One is the localizer, basically is the network to provide the location of the candidate box. And then we're going to use the ranker, basically is the real ID network with a strong discriminability to rank to the candidates based on the visual appearance respect to the query objects. Okay. Now, although this baseline seems to be working okay, but it still needs to further improve. So in this case, we developed so-called cyclic self-training framework. It is essentially to utilize the interplay between the localized and the ranker to improve both the representation of ranker and also the ability of localizer to identify the related objects. So as the first part of this framework, we have this ranker-based self-training approach, which essentially is to treat top rank results as a true results and use those pseudo labels for the top rank results to guide the localizer to better identify the related objects. And then on the second part, we going to turn the spin around and let the localizer to guide the training of the rankers. So essentially, we can apply the self-supervised training methods to all the objects identified by the localizers, and then use that data as the way to further improve the representation power of the rankers. So this is the evaluation we have done on two small data sets. One is instance 16, the other one is instance 335. The last two results are our results and the other results based on the existing competitive algorithms. Now, first of all, we quickly realized even our baseline results is better than the existing approach. This is really because our baseline results is based on the pre-training model from a large video sequence collected from various different data sets. Now, as you can see for the last line, with the introduction of cyclic self-training methods, we are able to significantly improve our baseline by 4% absolute values. Apparently, the instance search data set is relatively small data set. So in order to come up with more realistic evaluation of our approach, now we look at, we actually create two large annotated instance search data set based on public people search data set. So basically for these two data sets, we introduced a larger number of instances and also more variance on the object scales, aspect ratios, and also different type of objects that to be searched around, and more information as you can see from the last two rows of the tables. So now, when we apply the existing algorithm on this much diverse and much large data set, we clearly see that those conventional method does not work well at all on this two diverse data sets. But again, our baseline is a strong baseline, outperforms the other competitors. Well, the cyclic self-training method again give us 5 to 6% performance improvement compared to the baseline. So this again verify that even for more challenging data set we are facing, this simple cyclic self-training method seems to be the effective approach that we can rely on to improve the results of the instance search. Okay. All right, so, and then the next one, I like to talk about the representation learning. I particularly like to use the ReID as the way to illustrate the power of self-unsupervised representation learning. Now, for people familiar with the ReID, it's essentially comprised of the two process. In the first place, you're going to apply a supervised learning method to a large data set like ImageNet to learn a pre-trained model. So this learned pre-trained model will then be used as initialization to be fine-tuned to a ReID data set. So for both cases, we're using the supervised method. For the training, both the training and the fine-tuning, the supervised method being used in order to gain the appropriate representation for the images and objects. Then our first effort is to replace the supervised pre-training with the unsupervised one, which is the self-supervised learning method. So we know there are a number of different self-supervised learning methods being explored in various different articles. Here we are listing three representative ones: MoCo, MoB, and then Dino. So all these three methods are based on constructed learning. They probably differed in either the data augmentation method being used, and also they will be different as how to appropriate alleviate the problem of introducing negative instance. So now if we replace the supervised pre-training with the unsupervised pre-training method, this is what we see. So the very first row, as you can see from the table, is the supervised one with the results on the three different ReID data sets. And then compare between these three different self-supervised learning methods for representation learning, we somehow can see that turns out MoB seems to work worse compared to the MoCo and the Dino, and Dino among the three seems to yield the best performance for the ReID. But I would like to emphasize that this is just the empirical results, particularly for ReID, not necessarily can be generalized to other domains. So one thing that's been very encouraging is that even with the unsupervised pre-training model, the Dino is able to achieve similar performance as the supervised method from the table. Apparently, ImageNet has a large difference in terms of image content compared to the ReID. So we wonder that maybe we can utilize a more appropriate data set for pre-training models. So here we introduced the Lu person data set. This is the one being introduced in CVPR 2021. It comprised of 4 million unlabeled person images and over 200,000 identity extract from the YouTube videos. And the property of this data set is really diverse. It's diverse in terms of environment and also diverse in terms of capturing device, lighting variance, racial diversities. So all these diversities really helped us to build a much robust representation compared to use just the ImageNet data set. Now, when we introduce this new data set, the Lu person data set for unsupervised pre-training model, we can see for these three different self-supervised learning methods, their performance has been beefed up very significantly. So, and more important is that if we're looking at the Dino data set, turns out that this unsupervised pre-training model based on the Lu person data set is able to yield substantial better performance compared to the supervised method that work on the image data set. So this really implies that one is the self-supervised unsupervised pre-training mode method is very useful, and the second that finding the appropriate pre-training model, find the appropriate data set for pre-training model is also important. Then we challenge ourselves further by looking at the fine-tuning. So most of the fine-tuning methods previously are based on the supervised methods. And then So our thinking is that can we also replace that with unlabeled data? So this becomes unsupervised fine tuning. Is that possible that we can have a good performance even when we have no labeling information for the fine tuning stage? So the idea is, again, very straightforward. So we take the representation that's been generated by the pre-training method, and then we run a simple the clustering algorithm which generate the pseudo labels for different instances, and that pseudo labels will become supervised information allowed us to run the fine tuning process iteratively. So here comes the overall the results. As you can see, that for the so if we look at the category of the supervised case that is using the supervised pre-training model from ImageNet, now if we run the unsupervised fine-tuning method, we do actually see a very significant degradation in the performance, going from the at least by 20% in terms of performance gap. But if we come to the DINO, which is the totally unsupervised pre-training model, and we see that using the unsupervised fine-tuning, we can still be able to achieve a slightly better performance compared to the supervised one. Right? So this again indicates that sometimes, particularly for those instance level of matching and searching, turns out supervision may not necessarily be so important. Indeed, having a good set of unlabeled data and knowing how to utilize them most effectively to generate the best representation seems to give you a very good performance by the end of the day for the instant level of the matching and the classification. Okay, so then I'm going to come with the last piece of my talk, which is talking about the representation learning for the supervised. So based on the previous study, and as you can see, although we can see the power of unsupervised representation learning, but I think everybody will come up with the question, why on earth that we're going to have a worse representation with appropriate labeling information? So here's the simple comparison between the supervised and unsupervised representation learning. So for the supervised representation learning, the good side is that there's a clear supervised signal coming from the class assignment, but there was one downside that often is ignored or skimmed by most of the researchers, that for most of supervised representation learning, because the last layers of this classifier tends to require different data points from the same class to be close to each other. And this is the very convenient for the purpose of classification, but it did have the potential to damage the nature representation of the class, because often it's the case that each class may be comprised of a number of different modes of distribution, but pushing them into one single mode distribution could actually have damage on the representation. On the other hand, unsupervised representation does not have the problem, but it do actually have the issue, that is, it does not have any signal for itself to learn high-level semantic representation. So how can we, on one hand, receive the benefits of the supervised learning, but on the other hand, avoid this downside? So here's our proposal, and this is again still ongoing research. We call the leave one out KN classification approach. So the idea is the following. So what's so-called leave one out classification is that you're going to take any example out of the data set and try to use the rest of the data set to make prediction of the leave one out example. And then the prediction method we base is the KN. More specifically is the weighted KN. And in fact, you can write down very specifically the loss function based on log likelihood of the KN classifiers. And you can use this log likelihood as basis to train your model. Now, you may wonder why this simple replacement of the linear classifier that would be utilized in many cases with the leave one out KN would be a good idea to resolve all the issues with the supervised learning. So as you can see from this figure, so the left one is essentially showing that when you have this supervised representation learning, it is nature to push all the data points close to each other from the same class, try to push the data points from the same class to be form one tight cluster. But on the other hand, if you utilize the k-nearest neighbor leave one out classification as the loss function for guidance, you actually can alleviate this problem because for the k-nearest neighbor classifier, everything you need is to require the most of the nearest neighbors of each instance actually share the same class. So it does not require all the data points from the same class to form tight clusters. Instead, it actually allowed data points from the same class to form multiple different clusters. That actually helps us to preserve some of the nature representation of images. So here's some results we have done. Basically, we pre-train the method and our ImageNet 1K, and then the downstream task are the 9 different classification tasks. And so the first evaluation is based on linear fine tune. Basically, we keep the representation itself and then train a linear classifier to see the results on the downstream dataset. And so as you can see, the performance on some dataset compared to the supervised and also unsupervised is very significant, right? So so here we do see the self-supervised learning is performs better than the supervised, but if you come to the proposed method, we actually can see further improvement. Now, if we allow the system to be fully fine-tuned, turns out that the performance gain seems to be substantially less compared to the linear fine-tune, as you probably expected. So this is the visualization that I would like to confirm that our early hypothesis, right? So on the left plot, you see is that the distribution of data points coming from the supervised representation learning. So you see that all the data points from the similar class seems to form a tight clusters in most of the cases. But if we come to the proposed method, look KNN, turns out many of the class being split into 2 different clusters. So that's really indicates that utilizing the k-nearest leave one out the k-nearest classifier, you are able to avoid the issue of the supervised learning, which is to push all the data points close to each other to form tight clusters. Okay, so as the conclusion, so I just want to reiterate the simple points that is for the instant level of the searching, matching, and the classification representation is a very important issue. Now, as we can see, we have 3 different ways to guide our learning of representation. One is by the site information. Now, from the first few examples I saw in the image search, on one hand, it's important to leverage the site information, but on the other hand, it's very important to see how can you reduce the noise in the site information because those noise can actually cause a serious damage in the final representations. And the second part of the way to learn the representation is unlabeled data. And as we can see with the emerging of self-supervised learning method, there's a very powerful way we can learn a good representation out of the unlabeled data. And therefore, it's very important to take advantage of unlabeled data in this case. Then finally is the labeling data. Now, we used to rely on the labeling information to guide the learning of representation, but nowadays we see that simply utilize the conventional wisdom of learning from the labeling data may not give you the best representation. We need to give careful thought as how to do that And so therefore, it's very important to do the careful job to squeeze the best out of label information. With all, I would like to thank you for attending my talk. Hopefully this is useful information to your research and study. Thank you.
Thank you. Thank you very much for the great talk. So I think we have, yes, time for Q&A. And please feel free to ask questions on chat, or you can directly unmute yourself. So there is actually 2 questions on the chat, so we can start from those questions. So this is, I believe this is about image search part of your talk. So let me read the question. It's about the classifier. How many classes do you have? And it's a number of SKU class IDs.
So in our case, we actually build a data set which is comprised of roughly 100 million class. But one thing that I do actually want to emphasize that when you build such large data set, it is almost unavoidable to have a large amount of noise and errors. So we do find roughly 50% of data being annotated incorrectly.
I see. So please feel free to ask follow-up questions if that answered the question as well. So the second question, I think is also related to the image search, is that this is about the shelf recognition product on the shelf. Do you perform object detection and instance segmentation prior to the product recognition, which means is it 2-stage or 1-stage detector?
Okay, so actually I don't quite recall. So I believe we use the 2-stage detector, but I do actually have to check the paper. So if that's
Okay.
the question.
All right. And any other questions, or otherwise I can also ask some questions. So
Sure.
I'm actually wanted to learn a little bit more about the leave out one KNN classifier. So
Sure.
I think I'm trying to fully understand the make sure if I understand how this leave one out accomplish this this multi-mode of clustering. So yeah, so I was actually hoping that maybe that your classifier formula might explain it, but please feel to verbally also explain your method as well.
Okay, so I think first of all, for the standard linear classifier, the supervised learning tends to push all the data points from the same class to form a one tight cluster. That should be reasonable to understand for most of the people. Now, the reason the KNN has the power of allowed each of class of data point to be split into multiple classes is that for k-linear stable classifier, in order to make a prediction correct for each of the data points, everything being required is that for most of the k-linear neighbor of any data points, if most of those k-linear neighbors share the same class as the target data points, then you're going to have a very high accuracy of classification, which will lead to a very low loss of functions. So it only requires its neighbors to belong to the same cluster. It does not require all the data points has to be from one tight clusters. Do I make sense?
Yeah, understood now. So you don't really, like I say, introduce any special form of loss mechanism, but all you need to do is actually just use the KNN classification as your
Right.
loss function. Okay.
Right. So think about if you do like 5K, and then if you are able to be sure that the five nearest neighbors of any data points actually belong to the same class, then you're going to be good. So even though the rest of may not actually be the same class, right?
Yeah, makes sense. Makes sense. Thank you. And then, oh, there's another question on chat. So how to know which one sample to leave on out for that class?
Oh, okay. So in this case, we actually leave every single data point out. So basically, for every, so you go through every data point in the class. So let's say you take the very first data points out and you use the remaining data points to make prediction for the first data points, and then you go to the second one and so on and so forth. So for each of data points, based on this leave one out, you can write down a log likelihood function, then you can construct a loss function based on the log likelihood, and that become the basis for optimization. Is it clear? I don't know if I make.
Yes, yeah, the chat answered. Yeah, so that, I think that was clear. Yeah, thank you.
So I have another question.
Please.
Here, okay, on the same topic. So it sounds like it is important the way you construct the batches in this method, right? Am I right? Or can you provide some more details about that?
Can you clarify your question? You said that it's important to construct what budget?
Batches, like training in a mini batch mode, and actually how you sample the batches, because
Oh, okay,
I expect that for this to work, probably you would need to have
Yes,
like, like neighbors into the batch with the same label. Yeah.
Exactly. So what I did not write here is the detail of implementation. As you probably can imagine, you cannot do the full scale the nearest neighbors for large data set like ImageNet. And we actually even go with higher one ImageNet 21K. So you really have to do the construction about how to build the k-nearest neighbors. Now, just using the batch is not good enough. In fact, you need to create a special memory. And then if you create a special memory, then you're going to have some issues related to the discrimination of the encoder, because as we run in algorithm, the encoder become more and more updated. Well, and everything in the memory is still using the old encoder for generating the embedding. So you have to deal with that discrepancy and so on and so forth. So I actually leave some of the details out for the practical implementation without put over here. But if you are interested, I think we have archive drafts and I can share it with you.
Thank you. Yeah, thanks for the answers. Any? Yeah.
I was
please.
gonna have a question. Actually, the first thing is you said you have an archive draft for this. If you do, yeah,
Yes.
that sounds like interesting. If you can share in the chat later.
Yeah.
But I was gonna ask about actually the other part of the talk, the re-ID using domain adaptation.
Sure.
I was trying to understand a little bit more detail.
Okay. Which part?
I think it's so that I think the third part of the talk is re-ID using
yes.
unsupervised domain adaptation.
Right. So
yeah.
Right. Go ahead. Yeah. What question?
So here I was trying to understand. So when you changed to fine tuning
right.
With unlabeled data, because you're already doing pre-train, I think using, if I remember correctly, this
right.
other person data set, right? LU person or something like that.
Yes.
Yeah. Why isn't that already enough? I'm just trying to understand, because you're already pre-training on a data set of trying to distinguish different persons, right?
Yeah.
Are you going to fine tune with again to kind of like distinguish other different persons? Why is the fine tuning necessary? Maybe I'm missing something.
I see. Excellent question. So particularly for the re-ID, is very sensitive to many things. So for instance, it could be sensitive to how the camera can be figured out, right? Is configured. So for instance, you can have this top-down view and you can have side view, and also being sensitive to, for instance, the season. So for instance, if you have most of the picture come from summer, then you're going to people wear shirts and skirts. If you have the pictures captured during the winter time, then there are large diversities, and therefore I think based on our experience, customize the data particularly to the domain. When I see the domain mostly relates to the region, the season, the camera, and so sometimes actually camera has different calibrations, so you will see a very different different images even with the same captures. So for the Ray ID, it's actually very important to have this from the general adaptation, which is Lu person now, to this very specific adaptation, which very relates to the capturing of those person.
Got it. So if I understand correctly, the way that you're proposing here to do the fine tuning is by basically kind of like clustering the data and then kind of treating those clusters as classes. Is that right?
Yes.
Yeah.
So that's the basic idea. Yeah.
Got it. So yeah, that seems very interesting because some of the things we discussed in the workshop is first of all, it's challenging to collect the data, as you pointed out. Very tedious to annotate all this very fine-grained instance level things. And in another way that it could be helpful, I think, is that in many cases, some of the classes, they can have very different views of the same object, and sometimes this will not actually help. Now actually being more related to the last part of the talk, this will be kind of like multi-model kind of within each class, and it could hurt the performance actually when you're trying to do the learning. Yeah.
Well, thanks for the feedback. Yeah, I think that's good points.
Thank you.
Okay, so I think we are on time. So I would like to thanks again for Dr. Wang Jin, especially joining us at the very early time in your local time. And then, so I guess I will hand it over back to Andre to go back to our conclude the workshop.
All right, thanks, Jack. So